Reis opp. Ja, reis opp.
Welcome back, and good afternoon, and welcome to this public defense of the thesis entitled Investigating the Effects of Endurance Exercise on Protein Metabolism, with a specific focus on urinary nitrogen excretion. Today's candidate, Matthieu Clauss, completed his thesis in March 2025. And based on a proposal from the Department of Physical Performance, the Committee for Research Education has appointed the following committee to judge the thesis and other requirements for the award. Professor Olivier Sens, Norwegian School of Sport Sciences, Chairperson. Professor Emerita Eva Blomstrand, the Swedish School of Sport and Health Sciences, Gymnastik- och idrottshögskolan, Stockholm, Sweden, first opponent. And Professor Mark E.T. Willems, University of Chichester, United Kingdom, the second opponent. The committee has concluded that the thesis meets the standard worthy of a public defense for the award of a Doctor of Philosophy, PhD in sport science. Earlier today, the candidate has given a trial lecture with the title Plant-Based Protein, Is There an Application for Exercise and Recovery? The trial lecture has been found satisfactory by the examination committee. So I would like to ask the candidate to introduce his doctoral research in the form of a short lecture, and the opposing members of the examination committee to engage the candidate in a defense of the work. Should members of the audience wish to ask questions relating to the research, I ask you to bring these in written form to the attention of the chairperson, Olivier, in the break prior to the second opponent's questions. So please come up, Matthieu. The floor is yours. Thank you.
Yes. Perfect, thank you. Dear committee members, colleagues, family and guests, I'm honored to present my PhD thesis titled Investigating the Effect of Endurance Exercise on Protein Metabolism, with a specific focus on urinary nitrogen excretion. Endurance exercise increases energy demand, and to meet these needs, the energy system adapts and can increase energy production. The energy comes primarily from aerobic metabolism, which relies on oxygen availability. As exercise starts, the demand for energy increases, prompting the body to increase oxygen uptake. So at rest, the oxygen uptake is around 0.25 liters per minute, and in well-trained participants, it increases to 4 liters per minute during exercise, meaning that the order of magnitude of the change in oxygen uptake from rest to exercise is 16 times higher. And energy can be provided through the utilization of carbohydrates as an energy substrate. The rate of carbohydrate oxidation during exercise is around 2.5 grams per minute, meaning that from rest to exercise, the rate of carbohydrate oxidation is multiplied by 10. Fat can also be used as an energy substrate, and the rate of fat oxidation during exercise is around 1 gram per minute. Thus, the rate of fat oxidation is multiplied by 20 from rest to exercise. And the distribution of the contribution of carbohydrates and fat to energy production is well described, and is notably associated with exercise intensity. At low exercise intensity, fat is the main energy substrate for energy production, and when the exercise intensity increases, the contribution of carbohydrate increases, while that of fat decreases parallelly. And at high exercise intensities, carbohydrates are the main energy substrate for energy production. But there is a third macronutrient that the human body has access to, so what about protein? Studies often calculate energy substrate utilization from indirect calorimetry without protein oxidation. Indeed, knowledge about protein is more limited compared to carbohydrates and fat because protein metabolism is difficult to study. Protein are long chains of amino acids, and the human body uses 20 different amino acids for protein synthesis. Each amino acid has distinct metabolic pathways. And to measure protein metabolism, one of the main methods is to measure nitrogen excretion. Indeed, all amino acids contain a nitrogen atom in blue here, and its feature is shared by only a few other compounds in the body. And when amino acids are metabolized, the nitrogen is excreted and can be measured. The carbon skeleton undergoes further reactions to form compounds that are involved in energy production processes. Another method involves using isotopically labeled amino acids so we can track their path in the body. After the metabolization of the amino acid, they are found in several metabolites, and the carbon-13 enrichment in exhaled gas can be used to quantify this metabolization. The rate of protein oxidation at rest has been previously estimated, and by combining results from published study, we found it to be around 0.05 gram per minute for a 70 kilogram individual. However, the rate of protein oxidation during endurance exercise is not known. The question remains, what is the effect of endurance exercise on the rate of protein oxidation? And to answer this question, paper 1 was a systematic review of published studies and data. The inclusion criteria were the first, the measurement of protein metabolism with nitrogen excretion or leucine oxidation. Second, the inclusion of an endurance exercise condition and a control condition without exercise. And this was necessary to account for the obligatory nitrogen loss. The data collected during the non-exercise condition, they were subtracted from the data obtained during the exercise condition, enabling to isolate the adaptive component of protein metabolism and eliminate the obligatory nitrogen loss, such as normal daily turnover. Third, inclusion of a description of the endurance exercise protocol, duration and intensity, and endurance exercises were defined as running, cycling, or cross-country skiing session lasting at least 60 minutes. And finally, the inclusion of healthy participants over the age of 18. 30 studies were included for a total of 286 participants. And the aims of paper 1 were, what is the effect of endurance exercise on the rate of protein oxidation? And what is the effect of exercise intensity, duration, and volume on the rate of protein oxidation? So here are the results concerning the rate of protein oxidation. Each line represents an included study or participant group, and in the middle are presented the mean and confidence interval of the rate of protein oxidation. And it's possible to see that the rate of protein oxidation is increased by endurance exercise in all studies. All values were positive, and that there is a large dispersion in the results. The meta-analysis combined all these results into one estimate that indicate that endurance exercise increased the rate of protein oxidation by 1.02 milligram per kilogram per minute. This means that the rate of protein oxidation increases by 0.07 gram per minute during exercise, resulting in a 2.3 times increase from the resting level. So this is far lower than the increase for carbohydrates and fats. Concerning the second aim, an increase in exercise intensity on the x-axis was associated with an increase in the rate of protein oxidation on the y-axis. And the shape of the dots on the figure represent the measurement methods used, while the size of the dots reflect the weight assigned to the study or participant group by the meta-analysis. And there was also no significant difference in the rate of protein oxidation between measurement methods. And neither exercise duration nor exercise volume had an effect on the rate of protein oxidation. Exercise volume was calculated as the total volume of oxygen consumed during exercise, equating it with total energy expenditure. And this approach of exercise volume combined exercise intensity and duration into a single variable. However, the inclusion criteria in paper 1 limited significant variation in exercise intensity due to the minimum duration requirement of 60 minutes. So as a result, exercise duration was the primary factor influencing exercise volume. So in conclusion for paper 1, endurance exercise more than doubled the rate of protein oxidation, and also an increase in exercise intensity was associated with a greater rate of protein oxidation during endurance exercise, but neither exercise duration nor volume had an effect on the rate of protein oxidation. As presented at the start of this presentation, carbohydrates are a primary substrate during endurance exercise, and carbohydrate ingestion during exercise can maintain carbohydrate availability by maintaining, for example, plasma glucose concentration as presented here. It has also been shown that exercise with low carbohydrate availability increases nitrogen excretion while having the same protein intake. So this indicates that lower carbohydrate availability could lead to higher protein catabolism. However, to what extent carbohydrate ingestion influences protein degradation during prolonged endurance cycling has not been clarified. This issue was investigated in paper 2, where the aims were: can carbohydrate ingestion prevent performance reduction in subsequent exercise? And can carbohydrate ingestion impact protein catabolism? And the aim of the present study was to compare an exercise of cycling to exhaustion without an energy supply versus the same duration of exercise in which participants consumed a carbohydrate drink to prevent exhaustion. And based on previous studies with similar design, we expected participants to cycle longer in the carbohydrate condition. So participants were blinded in a single blinded design, and they experienced an exercise until exhaustion under the placebo condition at the first test to determine the quantity of work. At least 7 days later, in the second test, carbohydrate was supplied, and participants completed exactly the same amount of work before being stopped by the experimenter. So 7 well-trained participants completed the protocol and cycled in average for 147 minutes at 68% of VO2 max before voluntary exhaustion. And after 5 minutes of recovery, they performed in average 8 intervals of 1 minute work, 1 minute recovery at 90% of VO2 max. In this study, all meals were provided and standardized, and in the evening, a drink was provided in the evening to have an isocaloric design. The next day, they performed a time trial as a performance test, and in order to reduce the odor effect, participants performed a familiarization session before the intervention, and they were also blinded for the time during the performance test. To control for 3-methylhistidine, participants consumed a meat and fish-free diet the last 3 days before each intervention. Urine and blood samples were collected during the study period. Carbohydrate ingestion during exercise maintained plasma glucose concentration compared to placebo and also increased the rate of carbohydrate oxidation. Participants oxidized in an average of 81 grams carbohydrate with carbohydrate ingestion, more compared to with placebo ingestion. Regarding the first aim of this study, performance was better maintained the day after carbohydrate ingestion, and the 1-minute improvement means, for example, from the 1st to the 7th place in the Tour de France time trial this year. There was no difference in urinary nitrogen excretion between the conditions during and after exhaustive exercise. Concerning protein catabolism, urinary 3-methylhistidine excretion is a specific biomarker for the myofibrillar protein degradation of skeletal muscles. There was no difference between conditions. And tyrosine and phenylalanine are 2 amino acids that are not metabolized in skeletal muscles. And as participants did not intake protein before and during the exhaustive exercise, an increase in their blood concentration can be a marker of protein degradation. There was a significant difference between conditions as carbohydrates prevented the increase in concentration. So in conclusion, carbohydrate ingestion prevented exhaustion during a standardized cycling exercise and improved time trial performance the following day. Carbohydrate ingestion did not reduce urinary nitrogen and 3-methylhistidine excretion, but can the increase in plasma tyrosine and phenylalanine concentration indicate lower muscle protein breakdown? The absence of difference in urine nitrogen excretion in paper 2 that I've presented now was noteworthy. And additionally, since urinary nitrogen excretion was not measured at rest, interpreting this result is challenging. So there is a need for studies on the effect of endurance exercise on urinary nitrogen excretion. In addition, looking at the included studies in paper 1, it appears that there is a lack of studies with long exercise duration. And endurance exercise with long exercise duration represent extreme conditions that could potentially more accurately reveal differences in protein catabolism. So this issue was investigated in paper 3, where the aim was to investigate if 5 hours of endurance exercise increased protein catabolism. So in a randomized order, 15 young, healthy, moderately to well-trained participants, they completed 1 day of 5 hours of endurance-based exercise and 1 similar day with the same food intakes but no physical activity. The 5 hours of endurance-based exercise were as follows. So it was 1 hour of running, 2 hours of body weight strength circuit training, 1 hour of cardio endurance workout, and 1 hour of cycling to exhaustion on a stationary spinning bike. Urine and blood samples were collected thoroughly during the day. There was no difference in urinary nitrogen excretion between the 2 conditions, and there was no difference in urinary 3-methylhistidine excretion. This indicates that endurance exercise did not increase protein catabolism. We measured also sweat volume, and it was significantly higher during the exercise condition. In conclusion, 5 hours of endurance exercise compared to a condition without physical activity did not result in differences in urinary nitrogen or 3-methylhistidine excretion. However, sweat nitrogen was not measured. Including sweat nitrogen excretion would likely increase the total nitrogen excretion. Finally, the time resolution of urinary nitrogen excretion is not well described. For For example, looking here at the data on nitrogen excretion from paper 2. So if proteins are degraded during exercise, when can we expect their nitrogen to be excreted in the urine in this study? So can you expect it at the end of the day, or at the beginning of the next day, or a combination of both? This issue was investigated in paper 4, where the aims were to investigate what is the time resolution of urinary nitrogen excretion following an acute high intake of protein alone, and what are the plasma responses of insulin and incretins following an acute high intake of protein alone. So after protein ingestion, proteins are digested and absorbed as amino acids or peptides, which are then transported to muscles or to the liver for protein synthesis or metabolism. And protein synthesis is tightly regulated, allowing limited amino acid storage. Consequently, excess amino acids are metabolized with the nitrogen converted to urea and excreted in the urine. So thus, measuring urinary nitrogen excretion after a protein intake does provide a simplified model to investigate and quantify the time resolution of urinary nitrogen excretion. To the design, 14 young, healthy, moderately to well-trained participants completed the same intervention day while ingesting on one day a protein-only drink and on another day a carbohydrate-only drink in a randomized order. Participants arrived at the laboratory in a fasted state prior to ingesting the drinks, and no food was consumed until before lunch was provided at 12. Following lunch, there was another fasting period until 4 in the afternoon, and after this point, all meals were recorded and standardized between conditions. And the determination of the ingested dose, so 1.2 gram per kilogram, was meticulously designed. Given that participants experienced a prolonged fasting period after consuming the protein drink, it was essential to administer a sufficiently high dose to prevent a catabolic state. And this high dose also had the advantage to minimize the confounding variables such as variation arising from energy intake and dietary protein intake on the day before. And furthermore, there is also a notable scarcity of studies investigating the effect of higher protein doses on plasma insulin and incretin responses. Urine was collected in 6 periods, and blood samples were also collected during the day. The carbohydrate-only drink can be used as a reference to control for obligatory nitrogen loss and to minimize the influence of factors such as energy intake and prior protein intake on urinary nitrogen excretion. Treatment drinks were consumed at 8 o'clock in the morning, and hourly urinary nitrogen excretion was significantly increased from 2 to 4 hours after ingestion and from 4 to 8 hours after ingestion. Urinary nitrogen excretion was still elevated in the following periods, but in smaller proportions. It means from 8 to 16 hours after ingestion and from 16 to 24 hours after ingestion. And by subtracting the urinary nitrogen excretion in the carbohydrate condition from that measured in the protein condition and attributing this quantity to the ingested protein-only drink, we can calculate the percentage of ingested nitrogen excreted from the protein-only drink. And after 24 hours, 48% of the ingested nitrogen in the protein drink was excreted, indicating that protein metabolism is a prolonged process. Concerning the second aim, the metabolic responses to carbohydrate drink are well characterized, but it's not the case for a protein-only drink. Plasma insulin concentration was significantly increased by both drinks. However, while plasma glucose significantly increased following the carbohydrate intake, protein intake did not impact plasma glucose concentration. However, plasma concentration of all 20 amino acids involved in protein synthesis increased following protein intake, indicating that many of these amino acids contributed to the insulin response. Plasma concentration of amino acids were significantly higher than after carbohydrate intake, with the exception of cysteine. And the plasma amino responses for leucine, isoleucine, valine, alanine, glutamine, and arginine are presented here. After protein-only ingestion, plasma incretin concentration increased, both GLP-1 and GIP. So incretin, specifically GLP-1, that is glucagon-like peptide 1, and GIP, that is gastric inhibitory polypeptide, they are hormones released from the guts in response to food intake, playing a crucial role in regulating insulin secretion and glucose metabolism. Changes in insulin concentration were also significantly correlated with an increased GLP-1 response, which was not the case for GIP. Our results suggest that GLP-1 is the only incretin investigated that is likely to amplify the insulin response to amino acids. So in conclusion, ingesting a protein-only drink increased urinary nitrogen, mainly in the first 8 hours, but still until the next day, and also increased the plasma concentration of insulin and incretins. The overall conclusions for this doctoral work were: paper 1, endurance exercise increased protein metabolism and more than doubled the rate of protein oxidation. In paper 2, ingesting carbohydrates to prevent exhaustion during standardized exercise did not result in differences in urinary nitrogen or 3-methylhistidine excretion compared to a placebo drink. However, can the increase in plasma tyrosine and phenylalanine concentration without carbohydrate ingestion suggest a higher muscle protein breakdown? In the third paper, 5 hours of endurance-based exercise did not result in differences in urinary nitrogen or 3-methylhistidine excretion compared to a condition without physical activity. Including sweet nitrogen excretion would likely increase total nitrogen excretion. Finally, in the fourth paper, excess nitrogen following an acute high intake of protein alone was primarily excreted in the urine within the first 8 hours, but it continued to be excreted until the next day. The novelty of this research and its relevance to the athletic community can be summarized in 3 key points. Recognizing that endurance exercise significantly increases protein oxidation, it is crucial for athletes to adapt their dietary intake to support recovery and performance. Secondly, ingesting carbohydrates during prolonged exhaustive exercise can help maintain subsequent performance. Thirdly, protein metabolism is a long-lasting and adaptable process, highlighting the necessity for practitioners to adopt long-term strategy for protein intake. And as I conclude, I want to highlight how much I've treasured this time spent here with you. It has been a wonderful journey, and I look forward to future discussions. Thank you.
Yeah, thank you. And thank you for a good presentation and a good summary of your thesis. So before we sort of go into the studies, I just have a general question. What was it that sort of attracted how come that exercise physiology attracted your attention? So you decided to go into this and do your PhD within this field?
Yes. I think I've really liked since my childhood, I really liked both sports, and I also really liked how to improve, how to optimize things. So it was a good way to combine both of these hobbies. And then, for example, as we have tried here, but for example, with performance, how can we try to optimize performance? So to do these things, trying optimizing and applying in the sports condition was really exciting, yes.
Yeah, I agree with you. I think it's very interesting. So another little bit general question is that when I read both your summary and the paper one, you sort of all the time you write that you say that protein is an energy source. For example, you write that exercise performed with depleted glycogen stores heightens protein breakdown. These findings suggest that increased protein oxidation compensates for the energy deficit resulting from reduced carbohydrate. Is that what you really think? That protein is an important energy source, or when you have so much fat available?
Yes, actually, proteins, their main role is not to be an energy source, but as we've seen, it's possible to degrade them, and then amino acids can be used as energy sources, even if it's not their main roles. But then this degradation has consequences, because then we need to get these amino acids from somewhere, so essential or functional proteins. Mm-hmm. But I agree that is not the role of protein to be energy reserved in the body, yes.
Okay, so what do you think, what could be the reason for protein to be, or amino acids to be oxidized? Could there be any other reason for that?
Yes, I guess it's several reasons, but one of them is, for example, some others preferred energy substrate that are lacking, either at the whole organism perspective, but also locally in muscle or the liver. But it can also be sometimes, when I think about the Krebs cycle, sometimes some of the intermediates can be also lacking, and then, for example, amino acids can be metabolized to one of them, and so they can be used to make the whole energy system work without being the primary substrate.
Okay, yeah, no, I agree. I mean, I don't think we really know, but one theory is that actually amino acids are broken down to produce glutamine. Have you heard that?
Yes.
That's an old theory. I don't know whether it's still interesting these days, but to produce glutamine, which is a substrate for immune cells. So that, but I share your opinion that, of course, it's used. That's one thing. It's used as an energy source, but it could also be other reasons.
Yes, and also, for example, alanine is also like a little bit like glutamine. It can also be used to move energy, for example, from muscles to the liver, without being in itself the energy substrate, but just be used to move energy through the body.
Yeah. So if we go to the methods, you have inclusion criteria.
Yes.
There's one thing that I wonder is, were the subjects fasted overnight? Were the experiments performed in the morning, or were they performed at another time of the day? And was the initial glycogen normal? It's those two things
you mean
that
in the review?
Review paper, yeah, the ones that you had. You had a number of inclusion criteria,
yes.
And I can understand. I mean, it's not easy to look at if they were fasted or not. But
yes,
did you do that?
We included both published studies that had the rate of protein oxidation as an outcome, but we also included some studies that had enough data to allow us to calculate it. And so this was consequently, most of these studies, they were not standardized or designed to be optimized regarding the rate of protein oxidation. So that's why there is also a large dispersion in the results, because there was a large dispersion in the designs. So there were some studies fasting, some fed. There were some with low protein intake, some with high. Low energy intake, high energy intakes. It was also mostly males, trained males, but it also some studies with females and males, and some few, but with only females. So it was actually a lot of things that were put together, and I should say that the most interesting thing is not in the meta-analysis. I guess for me it's not the estimate, but our aim was to provide a review and to try to map the existing literature and then to put everything. And I think that the figure in the center with all estimates and their dispersion is giving more information than the estimate calculated by the meta-analysis that put everything together, but maybe not everything is comparable.
Yeah. No. I think it's a good study, because this is a question that I'm sure it will be cited a lot, because often when you have a general introduction, you write about how much protein is used, and so I think the approach is very good. I was just curious about whether there were any chance you could have had those inclusion criteria as well. So it's no big deal. I understand that it's.
It has been a lot of discussion, on what should be in, and also with the methods. We had, for example, nitrogen excretion and leucine oxidation. We had also the arteriovenous difference of tyrosine that we first included, and then one reviewer was against. So then we also took it away. But then, yes, there's been a little bit changes in what was included and not.
But you assumed that the urinary nitrogen loss is equivalent to or represent the protein oxidation. Is that right?
Yes, from the nitrogen excretion method, yes.
Yeah,
We had also this non-exercise condition. So as we calculated it, we had, for example, 1 day with exercise and 1 day without exercise. And then we took the nitrogen excretion during the 1 day with exercise minus the nitrogen excretion during the day without exercise. And then this difference, we said that it was attributed to the effect of exercise, and then we calculated the rate of protein oxidation from this.
But this assumption is based on the fact that you don't have myofibrillar protein degradation during the exercise. If you have that, then you couldn't actually sort of convert it directly to protein oxidation. I'm not saying it's wrong, I'm just wondering whether you thought about this, because if you have had a massive myofibrillar protein degradation, that would have been one part, and not only oxidation.
Yes, we also, it was not easy to find a term. The protein oxidation also, as we call it, sometimes could be, for example, from the nitrogen method, could be both protein degradation and protein oxidation. So then it was not that easy to find the right term also to...
No, I think you've done the right thing. It's not that. I just sort of, because there is no proof that you have you have no increase in 3-methylhistidine
No.
in the urine, so that is actually the reason why you could
Yes.
use the urinary nitrogen to measure protein oxidation. So I think you've done it right. I just wonder whether you have thought about the possibility that not all protein is oxidized.
Yes, we had, and then it was a part of this discussion with what is the right term, or what are we measuring when we get, for example, extra leucine oxidation or extra nitrogen excretion. What are we measuring?
Yeah. So I have just one last question on this paper, and that is, as you commented on, the protein oxidation as you calculated at rest is very high.
Yes.
And what is I think it is far too high.
Yes, I agree. I should say that maybe we should have been a little bit more cautious when writing it in this discussion, because it seems that we almost find a protein requirement recommendation. However, it was just calculation from the data that we had, and then as we needed both exercise and control condition without exercise, so we excluded also a lot of studies without exercise, so then these other studies were not included, so they could also have moved the requirement. And also, for example, we also based this calculation on for example, for nitrogen excretion, on the nitrogen excretion during the day without exercise. But some of this nitrogen that is excreted can also come from other sources, not only internal in the body. For example, in studies consuming food or protein during these days, some of the consumed nitrogen could be then excreted in this condition, then it will be higher nitrogen excretion on these days. Feeling so that.
Okay, so that could actually be a reason why you got so high, because the daily recommendation is 0.8 gram per kilogram, and that would be quite.
Yes, I'm aware of.
So 50, at least half or 50% lower than what you recommend. So I guess that that could be one reason, as you say. I just wonder, I didn't know.
Yes, that's why, because we did not find the zero nitrogen balance, but we used the data on the non-exercise days and then extrapolated the requirements from them.
Yeah. Okay.
But
I noticed that you'd actually comment on that it was high, so that's fair enough. So
yes.
So,
but yes, I should say that the most important thing from this review, and that I also advise people to use, is the increase from exercise or from rest to exercise, but then the level in themselves, starting level from rest, is maybe not.
I think so too. So
yes.
That's fine. So if we then move into study 2.
Yes.
Could you explain how you sort of reasoned regarding the experimental design in the study, and what was you said what the aim was, but what was your hypothesis, and how come that you actually used this particular design to answer your question about performance and protein degradation?
Our hypothesis was if they ought to do 2 conditions, and with one they should cycle to exhaustion, so it was the one with placebo, and then the other one they would consume or ingest the carbohydrates to prevent the exhaustion and just cycle the same amount of work, but without reaching exhaustion because of this carbohydrate intake. And then The hypothesis was that preventing the exhaustion would then induce differences in metabolism, like inside the body, and then the higher carbohydrate availability will be like the preferred energy substrate used, and then will spare or protect from the utilization of proteins. And then we would, with the performance the next day, we would like to see if sparing or not using these proteins, like having less protein catabolism, would be translated to performance differences.
But what would you think would be the actual mechanism behind this? The molecular, the mechanism in the muscle, for instance, how come that you will increase performance the next day?
Yes, so we found a difference in performance, but we did not find any difference in protein catabolism. So the mechanism should be another one that reduces protein catabolism between conditions. We have thought about two mechanisms. It was one that they had an improved recovery after the carbohydrate condition. As for example, we had some sprint tests. So we had the one between the warm-up and the exhaustive exercise on day 1, and we had the one before the warm-up and the time trial on day 2. And then on day 1, both conditions performed the same during the sprint, but on day 2, the performance after the placebo was decreased, while the one of carbohydrate was not significantly different from the day 1. So it shows that there has been some differences in recovery between the two conditions.
Yeah.
And we also...
I will get back to what you mean by recovery.
Yes.
I get back to you later on that, and we can discuss that, because that was also one of my questions. But when you talk about carbohydrate availability, but the studies that have shown an increased protein degradation are the ones where you have reduced muscle glycogen.
Yes.
And what you have is that you keep up the blood glucose, you supply carbohydrates. And so I'm just a little bit surprised that you didn't sort of try to manipulate the muscle glycogen.
Yes. That's true. The one, yes, for example, the one I used, it's like they perform a depleting exercise the day before. But yes.
No, I think it's so much work, and I'm really impressed by the work that you have done. And then you have just a very small, to my view, it's a very small intervention. And not just that, you do the best you can to stimulate protein synthesis after the exercise as well, by giving them giving the subjects in the placebo condition extra carbohydrates to keep up at the same energy. So I think you're doing whatever you can for not having a protein degradation difference between the two. Or do you agree or not?
Yes. As we had both these aims, protein catabolism and performance, so then we had also to find a balance, because without the evening drinks, then any difference in performance the day after would, probably because of any difference in carbohydrate ingestion or glycogen levels in the muscle. So we tried to have a balance or isocaloric design then that if we get some difference in performance, then it's related to what we were studying, like placebo versus carbohydrate.
Yeah.
But then I also, yes, I agree that, or especially with protein metabolism, often the effects are quite small, and maybe we are not giving us the best chances to see an effect by, yes, giving enough energy, and then also protein intakes were kind of high, so then participants were also in positive nutrient balance in both conditions. So then also, maybe it also led to no differences.
So you can say that your priority was the protein, was the physical performance.
Yes,
That was, yeah. And I think I think the design you have is intriguing, that you do exercise one day to exhaustion or near exhaustion, and then try to measure its performance the next day, because in my experience, to measure physical performance is the most difficult thing you can do. It's so difficult to get an effect on performance
yes,
compared to taking biopsies or blood samples where you can
yes, and
more
that's
easily.
true.
So I think the model you used and so much work you put into it, I just wonder how you could have done it differently to also having a hypothesis or a mechanism maybe to explain your findings, but maybe that's not possible, as you say, because you wanted to have an isocaloric situation. So
yes, it was quite dense. Also, protocol, it was really demanding, and we had also well-trained participants to have quite good replicability when they cycle to exhaustion.
yeah.
So then this also kind of participants, sometimes they're also reluctant to have muscle biopsies. So that's why we did not add another measurement on top of all the measurements.
Okay, so that's the reason that it was difficult to
Yes.
get the subjects to allow you to take muscle biopsies.
Yes, and also
Okay.
participants, some will not have been part of the design or the study if muscle biopsy were taken.
Okay, I see. I know it is a problem with well-trained athletes.
Yes,
So and so. Okay.
some of them were really interested because some, like the protocol, 1 gram per kilogram per hour of carbohydrate was something, for example, they can implement in their own competition or training.
Of course.
So they were really willing to test themselves and to see if there is any performance effect. They were maybe a little bit less interested in the mechanism and like the physiology around.
Yeah.
So then, yes, biopsy were maybe not their first priority.
No, I understand. I mean, of course, they're interested in their own performance. They don't want to let you take biopsies. So that is, I think, one thing you have to consider, of course. So these subjects then, they were well trained and they exercised until exhaustion.
Yes.
And how? I don't understand how they can cope with 1 minute exercise at 90% after an exhaustive exercise for a couple of hours. How did they cope?
They had 5 minutes of recovery.
5 minutes. That's not much. Yeah.
We discussed also with them, and when they reached exhaustion, it was some of them explaining like a strange feeling, like they were not able to cycle more, but they still found like their legs like functioning, or they were still able to have quite high power. And some of them really appreciated to be able to maybe use a little bit more watts, and also to get this kind of intervals that are maybe a bit less demanding for the brain, or maybe a little bit easier to get your focus on something. You need to cycle 1 minute and then you get the recovery, while the other one is cycle as long as you can, and then sometimes there were some up and downs when they were cycling. Am I finished or not? And then they managed to cycle a little bit more. But I guess all of them, when they were exhausted, they were really exhausted. So we managed to.
Do you think of any possible reason, sort of more specific to the muscle, why they can cope with this type of change in exercise intensity?
Yes, so I can think that they possibly use different muscle fibers, like
that's what I
the
thought.
one the 68% of VO2 max seems a bit strange, but we had some pilots trying to find an intensity that is difficult, but you can still maintain it for 2.5 hours. So that was the aim. So we had some tests, and then it was really interesting because at this range of intensity, we tried, for example, 70 and 73%. And even if it's only 5% and it was 10, 15 watts difference, then it was way shorter exercise. And then we tried one with 65, and it was like almost impossible to finish. They were capable to cycle really long.
Forever,
So I think we managed to trigger or to use their muscle fiber one, maybe in this case, and then when they switched to the 90% that were a bit more intense and way more watts, then maybe the fiber type 2 were used.
Yeah, that's what that's what the answer I wanted, actually, because that is the only thing I can think of. Of course, you still have, I don't know how much glycogen they empty during, if they are well trained and cycle around 70%, they might not empty, but they probably empty selectively type 1 fibers, and maybe not all, of course, but I mean enough to not be able to go on, and then you still have glycogen left in type 2 fibers, so you can, and as you say, also mentally it could be easier without 1 minute.
Yes.
So
they were really competitive, so they also really like to push themselves.
Yeah.
So also this kind of format they were also used to, more than the other one, like with no clear goal.
No.
So it was also maybe a little bit trigger, like mental also.
But what's your feeling? They came back a week later and were served carbohydrates. What is your feeling that how long could they have cycled in that condition? Could they have cycled for another half hour, or could they? What's your feeling for what was the difference in fatigue?
Yes, it was of course some differences between participants. And between the participants, there are some that, when they were at the same point, when they were stopped with the carbohydrate, they told us that they were almost at the point of exhaustion. So some had small effects, but some felt like this was way easier this time.
Okay.
And even if, yes, we have the RPE data and we do not see that much often, or at exhaustion at least, they still point the same grade on the scale, but some said orally that they felt that it was a difference also.
Okay, so how come? Because that also surprised me that they rated the same on the Borg scale, because you would have thought that it would have been easier the second time. So that surprised me a little, and you had also in your conclusion here that it prevented exhaustion.
Yes.
So is that because of the instruction they get? It's not easy with the Borg scale. I think that physiologists are not so careful with explaining actually the Borg scale and the different sort of numbers you rate. Or
Yes, we
so
were
to-
also expecting and like talking to them after or on these days. They clearly said that they were feeling that it was easier on the carbohydrate day,
Yeah.
but then it's maybe it was single blinded, so we knew it was carbohydrate, they did not know. And then maybe it's maybe how we gave information to them, and then they thought that they had to cycle to exhaustion on both. Or to maybe they maybe felt the need to say that when it's finished,
Okay.
I'm exhausted.
Yeah. Yeah.
So, but
Maybe
it's difficult to interpret. We were
You-
expecting actually.
The single blinded is that the subjects didn't know. Is that what you mean?
Yes,
But you knew.
yes,
Okay. And I don't think that mattered, but someone else could have made up the drinks for you. Anyway, you know that the first time is the water condition.
Yes, it was
That's
because
right.
of the
So
design.
sorry, it doesn't matter. It doesn't matter because the first one is the placebo and the second one is the
yes, and
carbohydrate.
before doing the study, we also thought of maybe doing three times the intervention, like double-blinded, like carbohydrate and placebo, and if there is a too high difference between the 2 times to exhaustion, then do a third time with a carbohydrate and stopping at the same with placebo.
Okay. Yeah.
But it was actually really demanding for them with 2, so then
Yeah.
we just gave up the
Yeah.
third time.
I mean, you can't do everything. I mean,
No.
you have to do priorities, and I accept the priority that you said about performance because that's clear. That's been your number one priority. So you calculate protein oxidation and you give the results. And it's 25 and 28 grams. And how did you calculate that? Because the reference you gave wasn't very easy to calculate from.
This was from the nitrogen excretion during
This was from,
exercise. So from
I think you referred to Jekendrup and Wallis or something.
this,
So
yes, but then
okay, you calculated from the nitrogen
yes,
excretion.
because we
Okay.
collected in 4 periods, so we collected like from midnight to the start of exercise, all during exercise, and then they had to pee after exercise, and then we started a new collection period like to the end of the day, and then
Yeah.
a new from midnight to start of the performance test.
Yeah.
then
Okay, so that's how you calculate it.
Yes, from
Okay.
nitrogen excretion.
Okay. Yeah. Yeah, it wasn't all clear because you referred to a paper, and but I just wonder. But
Yes,
that's
but
fine.
Yes, in the paper they also calculated it from nitrogen excretion.
Okay. Okay. So you sampled, as you have here on this. You have it four different periods,
Yes.
and why didn't you measure 3-methylhistidine in those 4? You had aliquots that you froze. Why didn't you measure 3-methylhistidine in all those 4?
Yes, it was mainly from financial reasons. So we did not have enough money to measure all samples from all participants from all periods. But then we had to take a choice, and then we decided to pool them to have less samples. So then it was
So is that expensive then to measure 3-methylhistidine? You measured amino acids, and you maybe not in the urine, but it isn't expensive, is it, to measure, to do an HPLC and measure 3-methylhistidine? Or was that the real reason? You mean you couldn't afford that? Because that would have given a lot more information that would be interesting for the study, I think.
Yes, it was one of the main reasons, and also we were not certain that this short period, for example, exercise was like around 4 hours, that they were long enough to induce differences that were visible between the conditions. So then we also thought that pulling into one sample, then we will possibly increase the difference, but it can also be that there is some compensatory mechanism that, for example, it was lower with carbohydrates during exercise and then higher
I think that
after, and then placebo, and then we...
but that would have been very interesting, I think, to see that if you got this decrease and then a rise, and so because I don't know how if it is precise enough, but it could have given a lot more information, I think, into any possible protein degradation, which was one of your aims. So that I just wondered, because I was very curious about what it looked like.
Yes, that's true.
But you also have problems with the measurements, I guess, because they are too low.
Yes.
So who measured those for you then?
It was the University of Oslo, but
since it's for some reasons they are I mean, far too low. So I just wonder what happened with the assays.
Yes, I'm unsure why they were low values. We maybe hypothesize that maybe during exercise that they maybe retain, or they were like lower excretion, then that's why they were low values. But then as we pulled, so it was like 21 hours in one sample, so then this lower excretion during exercise should have been compensated, or at least have been excreted the next morning. So I cannot really explain why.
Because I mean, you actually did the effort of letting the subject go on a meat-free diet for 3 days.
Yes.
So you could measure 3-methylhistidine. So that's why I would very interested in to see how it turned out, because it's not so much data on that in the literature.
No.
There's some older studies, but this is a standardized experiment. So, but okay, this is what you had. But
Yes.
so so you also had the major finding is that the performance improvement.
Yes.
Yeah. And you also had these measurements of tyrosine and phenylalanine.
Yes.
And you have an increase. You have an increase of phenylalanine and tyrosine, and
yes, it was an increase
not
with placebo, but not with carbohydrate.
The carbohydrate,
and it's increase in concentration. So then it's
But why did you show the sum of them? Why didn't you show them separate, or one of them? Why did you show the sum of them?
It's because they cannot be metabolized, but phenylalanine can be.
Yeah, I know, but I
tyrosine.
just wonder why you didn't show tyrosine separate and phenylalanine separate, or just chose one of them. So it would have been easier to understand, but...
Yeah, so it was actually an effect on both.
Yeah, no, they follow each other, so
And then we're thinking that, yes, you can present the effect on one and then for example, expect, but yes, if we are both, yes.
No, and then you write that you cite two of our references and say that we didn't measure plasma.
Yes, or did you not measure arteriovenous differences?
In one study, but the two ones you referred to is one that we had arterial concentration of tyrosine and phenylalanine with and without carbohydrates. And the other one actually shows tyrosine.
Okay, yeah.
But for some reason we didn't show phenylalanine, which I don't understand. But we have tyrosine and they follow each other. So in both those studies we actually measured tyrosine and phenylalanine in plasma. And
Okay,
in
yeah.
one of them in muscle. And we didn't see this effect, as you see. So that's why I'm pushing you on this here, because we saw an increase in both conditions.
Yes.
So no effect on carbohydrates. But we actually measured them. That's just I had to look for myself when I saw what you had written there. So I had to go back to our studies because we always did that, measure plasma and muscle as well in most studies, and it goes up in the muscle as well.
Yes.
So so you think that would be a sign of a smaller degradation when you give carbohydrates, or no degradation when you give carbohydrates, and the degradation of protein when you see the increase in tyrosine and phenylalanine.
Yes, that in some way carbohydrates prevented the degradation that happened in the placebo.
Yeah. And then you didn't. You looked at the Fehlig and Warren study, and I think it's right that you say it could be a release from the muscle, but that hasn't been shown in a couple of studies. But it could also be a released uptake by the liver, and then you calculated how much it would be. And that sort of, if you could sort of walk me through that calculation, how you ended up with.
Yes, so of course that we did not measure the arterious-venous difference, so we were not sure that if there is more in blood, if it's because it's released, or if it's less uptake some other places. And then Fehlig, yes, they did with the liver that there were some uptake at rest, and when you exercise, the uptake was still, but a little bit lower, and then they from these two data, at rest and at exercise, we calculated like the reduction in uptake, and then we got this uptake per minute, and then we tried to extrapolate from how long they cycle in our study, like 147 minutes, and then find the quantity that should be taken up in the liver and see if this difference could
I didn't find the same. I mean, they had an uptake of about 5 micromolar per minute in the resting condition, depending on which of the two amino acids you take. But take one, and it was only 1.5, I think. They actually express micromole per minute.
Yes.
So they have included the blood flow and everything. And I couldn't get that would be quite a high number if you have this, 3.5 micromolar per minute, and you exercise for 2.5 hours.
Yes, so it's you say from 4.5 to 1.5.
Yeah. So
it's like 3 times.
Multiply by 200. What did you have? 247 minutes. Or
yes.
So that's quite a large number. So I'm not actually sure that it actually could mean that the uptake still is the reason for this increase. Why, I don't know, but...
Yes, that's true. Then we will be
well, I might have done it wrong. I just couldn't really follow your calculation there.
Okay.
But
yeah.
I think it's a good way of looking at it, because those studies performed in the 70s, I mean, they were such elegant studies, and no one is doing that today,
No.
I think, to put catheters over the liver. So it's very useful information.
Yes.
So I think it's a good comparison. I just sort of because we didn't get these differences, I'm just curious about why you got them. What is the difference between our?
Yes.
It's different subjects, of course. We had well-trained, but not athletes, but they were well-trained cyclists. But maybe your subjects were more well-trained, or you had more standardized diet. I'm not sure, but it's a difference that I.
Yes, if I remember well, they did not exercise to exhaustion in your protocols.
Sorry, when?
Did they exercise to exhaustion? Oh, I think it was 2 hours.
Yeah, it was. I've forgotten now. I think it was.
Because I think it was fixed, and then we had also some studies here, and then with also cycling to exhaustion, and then when comparing the amino acid responses in these 2 studies with exhaustion here, with yours, with almost the same intensity, but the responses were higher.
I think maybe we had a model where we exercised for a certain period and then they exercised to maximum, or I've forgotten actually, but
yes, it can be at the end. Yes.
Something like that. So it's a different model. That's right. So that could be one reason why it differs. But even if you don't have a release during exercise of tyrosine and phenylalanine from the muscle, you have a release in the recovery period.
Yes.
So that could maybe affect. I'm not sure the carbohydrates maybe, but you took samples directly after the exhaustive exercise.
Yes,
did you?
it was before and after exhaustion, and unfortunately it was nothing in the evening and nothing in the, or we did not measure in the morning the day after.
Yeah, and just to finish off with the branched-chain amino acids, which I think is interesting. I mean, you get a decrease in the branched-chain amino acids in plasma with carbohydrates, but no decrease when you in the placebo. Is that right?
Yes, it is.
And I mean, to me, that is opposite what you would expect, I think. Isn't it?
Oh, we were surprised. We were expecting, yes, the other way.
No, I think that, I mean, at least if you have low carbohydrate availability in the form of low glycogen, then you activate the branched-chain keto acid dehydrogenase, which means that you oxidize more branched-chain amino acids. But you see the opposite.
Yes.
When you have enough of carbohydrates, but it's still in the blood, so it might be a difference. And then you see this decrease, which I would have thought it would be the other way around.
Yes, it was the same for us. We were expecting the other way.
So that's it's intriguing. I don't know. I just think that you write something about that could be stimulating the rate of the TCA cycle.
Yes, or I was meaning that the TCA cycle was, or as carbohydrates, exogenous carbohydrates were taken with the drink, that they were primarily through the TCA cycle, and maybe some of the intermediates could be depleted, and then the BCA will be used to support this.
You mean support, so not actually changing the rate?
No.
Or did you mean that the rate of the TCA cycle was changed or not?
No.
No. Okay, I'm with you, because the TCA cycle regulates the oxygen uptake, so, and you had no difference in oxygen uptake. So you mean that it could actually supply, there should be
Yes.
the metabolites in the TCA cycle to help. Okay, yeah, that's fine. Although I still think that it's more of the rate limiting step will be the sort of oxidation maybe of the branched-chain amino acids, but
yes, absolutely.
You don't know. So this is now it's you just wonder why you get different results from similar studies, but I mean,
yes, we do
the
not
experimental
know. Yes.
design is different. So
Yes, the other way would have been a little bit easier to interpret, or at least maybe more coherent with
But this is the fascination, with science, isn't it?
Yes.
That you try to find which is correct, try to find an explanation for something, and you have to sort of, it's very good or very, very good to have a sort of wide hypothesis, so you could actually not too narrow, too wide hypothesis that you can modify throughout the work you do throughout the years. So that's just a sort of good way, I think, when you work. Don't be too narrow. Have a broad hypothesis so you could change, and so that's just an advice. So I think I'm happy with this, and so thank you. It's a good discussion. So I leave to Mark here. Yeah.
I guess.
Thank you. But before Mark's part, we will have a short break. Yeah. So thank you, and I think you will find coffee and some refreshments. And we will see each other again in 15 minutes. to the second opponent. Mark Williams, please come up. The floor is yours, together with Matthieu. So we're looking forward to the second part of this. So, please.
Okay, thank you very much. Matthieu, it's a great pleasure to stand here and being able to have questions for you on your PhD work. I applaud you that you completed your PhD here at the Norwegian School of Sports Sciences, which has a great reputation in Norway, but globally as well. So that's a great, great achievement. My questions will be having a slightly different tone. Some of them will be quite general, sometimes really specific. I think some questions, yeah, you can answer those in an objective way. Maybe some questions, I don't mind if you speculate and put some personal views in there. That's perfectly fine with me. I also prepared the questions without the use of AI technology. So all the questions that you get, that's me thinking that is a valid question. Now, the first opponent was questioning you on paper number 1 and paper number 2, and I'm going to ask questions on paper number 3 and paper number 4. But before I do that, I'll take you back to one of the early quotes that you have in your paper, in your thesis, of Le Mans et al., 1984. And let me, for those in the audience, let me read the quote. And we are talking about 1984, which is how many years ago? Yeah, quite some years ago, 41, right?
Yes.
So in conclusion, despite the fact that protein metabolism during exercise has been studied for at least 100 years, considerable confusion still exists. Well, the quote goes on. Do we still have confusion about protein metabolism during exercise?
Yes.
Before you continue, why did you choose this quote?
Yes, because it was one of the researchers that had a lot of papers on protein and was really interested in protein metabolism, but also when reading on protein, this period, 1980, was really active. It was a lot of new discoveries, and I think the knowledge increased quite a lot, and I think it's good, but it was kind of paradoxical that they were so enthusiastic that they think that everything should be soon resolved, or everything will be found out. And then, I don't know why, actually, but then it seemed that the dynamic went a little bit down about protein after these years. Maybe different research groups that were maybe not so interested, or maybe these results came, but they also came some limitations, so people did not find them so relevant, or did not put too many energy to go in this field. But I really like that they had this enthusiasm, and that today, like you said, 41 years later, we still have some or most of these questions that are still maybe not unanswered, but there are still some questions about the responses.
Yes. So it's a quote that is still valid today.
Yes.
And may remain valid for some time. I must applaud you on the fact that you undertook your work on protein, because as you said very kindly, maybe research groups were not that interested, but as we found out in the first hour of questioning, it's a very complicated area.
Yes.
And maybe that's why people are reluctant to wander into that. So I applaud you that you did that. Okay, let's move to another general question. And you used in your 3 intervention studies, you used, well, in paper number 3, different exercise modalities, but in the other studies, cycling as the exercise modality. And when you do those studies, you want to reduce variation to the best you can. You do it under standardized laboratory conditions. My understanding is you're from France, right?
Yes.
So we have the Tour de France in France, which is an event not really under standardized conditions. So what effect do you think it had on your observations that you had laboratory temperatures of, I think you maintained it at 18, 90 degrees?
Yes.
What were the consequences of that, I think, with respect to the findings that you had? And you can focus on study paper number 3 and 4, or go back to 2 if you like.
Yes, of course, it's always a question, like the transferability from our lab to the field. As we were both, for example, as I've told with paper 2, we were both interested in performance, but also a bit physiology, or a bit more metabolic explanation. So then we had also to find a compromise between having some effect on performance, but still have enough control conditions that if there is an effect, we can find some mechanism to explain it.
Yes.
And it's maybe then a little bit more difficult to transfer, like the 1 minute, and as I've said, it's like from the 1st to the 7th place in the Tour de France, but it maybe did not mean that if you drink carbohydrate, then you will improve that much in the Tour de France next year. So yes, the transferability and then the size of the effect is maybe not straightforward, but at least it's well controlled, and then we are maybe a little bit more sure that there is an effect, and then the size of the effect should be then measured on the field, I guess.
Yes. And you did measure sweat rate, and there was a reason for doing that. So obviously that is something that is very different if you would have environmental conditions that are in the low 30s or high 20s. So did you have any consideration about that, with the importance of sweat rate measurements for your studies, that you were still did those studies where there was not the sweat rates that you would normally get at higher environmental temperatures?
Yes, or if the difference, or if the temperature were more extreme, then we would expect the effects to be more extreme.
Yes.
But then, yes, or we can call it, in a way, a pilot study, because then, for example, with sweat, as you pointed, we only measure sweat rate and not the nitrogen.
Yes.
So then, if it has to be done again, nitrogen should be measured, and then it will be valuable for this design. And then, if the goal is to get the results for other weather condition or temperature condition, then it should be maybe a series of experiments to then find the effect. It has been some studies on nitrogen excretion in sweat, And it was actually the protein intake and the temperature that explain, or that the most parameters explaining the difference in the nitrogen excretion in sweat.
Okay.
So that's why we try to standardize
Yes.
in regard to these two parameters.
Yes.
But then, if it's then your goal to study the effect on the
Yes.
temperature, then should be a new study design. Then
It should be, yeah. Okay. Thank you for bringing up the design of your of paper number 3. You were reading my mind because I was going to ask for that. So, so I'm a bit confused, and help me out of this confusion, because you when you had the control condition first, you had a dietary intake that was matched when they were coming back for the experimental condition, and then they were allowed to have snacks, protein-free snacks, in order to...
yes, but only during the exercise condition.
Yes. But you had also individuals being tested in the exercise condition first. And then, so how do you match then the energy intake when they were coming back for the control condition?
Yes, so everything was matched at the end. The exception was the snacks, actually. So the snacks were not matched. And then this was done because some studies, they found out when they studied the effect of exercise, they found an effect of exercise on nitrogen excretion. But if the participants consume energy, so increase the energy intake, that was at the same amount that they calculated energy expenditure, then the effect of exercise disappeared. Okay. And then it seemed that it was more the effect of negative energy balance that led to the nitrogen excretion, or the increased nitrogen excretion.
Yes.
And then we tried at least to give them the possibility to eat some snacks and to encourage them to eat enough to be in the same energy balance in both conditions.
Okay.
But we failed, and then they ate these snacks, but it was not enough to compensate for the energy expenditure that was quite high because of these 5 hours.
Yes.
So they did not manage to eat enough.
Yes.
So then this part of the study that we wanted to study a bit the effect of energy balance was not easy, because there were still a negative energy balance with exercise. A little bit less because of the snacks, but not enough to be in the same energy balance in both conditions.
Okay. Okay, thank you. Moving on to another issue of the selection of your participants. You have in your studies males and females.
Yes.
That creates variation, I guess, because metabolism, physiology in women is different than in men. How comfortable were you with having women and men in your study? And did you have any consideration of just going for women only or men only based on their differences in the handling of protein and protein metabolism?
Yes. So in paper 2, it was only men, but paper 3 and 4 was both men and women.
Yes.
And then paper 2, we discussed it, but it was a bit more mechanistic. So then we tried to reduce the factors that could induce some variation. But then paper 3 and 4 were a little bit more general, or they were designed after the results from paper 2, like the things that we thought that were maybe challenging or a little bit not worthy from the results from paper 2, and we thought that inclusion of both men and women would not impact the aims we had in these two studies. So in paper 3 we had both men and women, but actually we did not manage to recruit too many women. I think it was
Yes.
only 4.
Yes.
So then it was not possible at the end to control for any
Yes.
sex effect or to come with some hypothesis about differences.
Yes.
Paper 4 are a bit more balanced, so then it was possible to study after with our data, even if it was not an aim before the
Yeah.
conducting the experience to study sex
Yes.
differences, but at least we had a bit more balanced data, so then we were
Yes.
at least able to control for it.
So you had women in the study
Yes.
of study number 3 and 4, and it is known, and there's no consensus about it. But for example, if you would look at fat metabolism, there's particular influence. Again, no real consensus that the phase of the menstrual cycle could have an impact on when you do your measurements. Did you have that consideration when you had females in your study, that you were they using anticonceptives, were they having a regular menstrual cycle, were you testing them in the same phase of their menstrual cycle? Could that have mattered for the measurements that you did?
Yes, I'm aware of these articles and all this data, but actually in these studies, paper 3 and paper 4 either, we did not took we did not control for this.
Okay.
In which proportion it has impacted the results, I don't know so much, as this study has only 4 women
Yes.
participants, so I don't know if it has
Yeah.
impacted, and then it was not so easy also to do any statistics after when we had the results,
Yeah.
because of on the small number.
Yes.
But yes, if it should have been
Yeah.
done one more time, then
Yeah.
absolutely, yes.
I don't know the answer to that, but obviously, it is something that maybe not in these kind of studies, but with other studies, there is a view out there that you need to control from when you do your measurements in which phase of the menstrual cycle. Let me move on to another general question. I read a lot that you had a balanced design, and people differ on what that means, whether that's related to the measurements that the participants get in each condition, but sometimes there's also balancing for particular physiological parameter. So what did you mean exactly by balanced in the design of your studies? And I think you did that for all the 3 experimental intervention studies. It was always a balanced design. So what did you mean by that, and why was it important to have that in your design?
Yes, and by balance, we meant to have almost everything equal, excepting the things that we were investigating, for example, dietary intakes. But in these 2 studies, 3 and 4, that were randomized, also with balance, we also meant that half of the participants started with one intervention and half started with the other. So we managed to have 8-7.
Yes. Okay. Yeah.
So
okay.
it was, but then paper 2, yes, then it was, as it was not randomized, everyone had placebo first. So in this way, then it's not.
No. Okay. Yeah. All right. So you want to keep things equal. You want to reduce variation. But all these studies have always so-called confounding factors, things that you could not control and could have affected your observations. So what do you think in study number 3 were confounding factors that could have potentially had an effect on your findings? And why do you think those were confounding factors?
Yes. As often in protein metabolism study, protein intake is one of the key factors. And then we decided not to have an imposed protein intake, not to say that everyone should eat 1 gram per kilogram per day, for example, but we decided to have all participants to follow their normal dietary intakes, just to get rid for any habituation periods or some effect that were maybe related to changes in protein intake rather than the effect of exercise. So then, yes, we had different participants, and then they had almost all their own protein intakes. So then this could, of course, influence like the results, like maybe the one with high protein intake have no effect of exercise, and the one with low had an effect of exercise. So I don't know, it was not possible. We did not find any correlation in our data after, but then, yes, it's maybe should have been, or it could have been designed differently then, but I don't have the answer on how it has.
And in paper 3, where you measured sweat rate.
Yes.
And you used a modified equation for sweat rate. Why was there a need to modify the equation? How did you modify it? And what was the reason to modify it? So can you elaborate a bit more on that you had to modify the equation for sweat rate?
Yes, or actually the equation we used was already called modified equation. So then it's not my own modification.
Oh, sorry. Okay.
We used the modified formula, and then, but then they had this need for modifying the equation because before sweat rate was, or the estimation was maybe a little bit easier. It was mostly on weight differences. And then they modified it to have for example, the water that was also excreted through the respiration, and also the substrate utilization that also caused a little bit of this weight change. It's not because it's sweat, but it's because some energy substrate, for example, glycogen, has been metabolized, and then they have been breathed out, and then you go a little bit down in weight without it being attributed to sweat.
And in study 3, you did measure urinary nitrogen excretion.
Yes.
In study number 3. That was probably your expected or hopeful outcome, that you would find a change, and it did not happen.
Yes.
Did you see that coming, or did you analyze all your urine samples in one go and then had the finding of it's not changed? How did you go about the analysis of this?
It was in one go, so we collected everything, and then everything was frozen, and then we transported it to the University of Oslo, and then
Okay.
we used their laboratory to measure it, and then. But I agree that it was the one that we were like, not maybe sure, but then we were like expecting it a lot,
Yes.
at least to get the different, and we saw that we went quite hard with 5 hours of exercise,
Yes.
that this
Yes.
should be at least more than enough to get some differences. And
Yes.
at the end of the article, I've included a table of a lot of previous studies, and
Yes.
some of them, or most of them, found differences, and some
Yeah.
with less demanding
Yes.
exercise. So
Yes.
I do not have a
You're
good
still-
explanation, but we were expecting,
And you're still puzzled by it, right?
yes.
And so if there is one thing, or, well, let me give you the opportunity to change a few things that you could have done differently in that particular study, what would you have done differently and why?
Yes, so obviously we would have measured the sweat nitrogen excretion.
Right.
There's been some studies indicating that sweat nitrogen can compensate for the urinary nitrogen excretion. Instead of being in the urine, it's like in the sweat. I don't know so much about the protein intake. I do not have so many intuition that it would change the results by imposing one common protein intake for all participants.
Okay.
And if we had to do it once again, I would really like to be able to give enough snacks to be able to be in the same energy balance.
Okay. Okay.
Because then, yes, I think we failed on this. We tried, but
Yes.
it
Yeah.
was not enough to get the same and then be able to discuss
Yes.
the other.
Okay. Now let's move on to the urinary trimethylhistidine, which you highlight there now. I was quite surprised to see, in general, in your thesis, that you have statements about the cohort effects. You do mention that some of the information that you have may have application for personalized nutrition, whatever that is, we'll get to that. But if you look at the figure here on the right, there's quite some variation in observations, and actually there's 2 individuals who clearly increased their 3-methylhistidine excretion. You know, the 2 data points there at the top, right?
Yes.
So what's going on in those individuals? Why do they respond so differently to the exercise protocol and to the intervention?
Yes, and I should say that in this study, we did not have, like in paper 2, the 3 days before,
Okay.
with the control on our meat-free and fish-free diet.
Yes.
So possible explanation will be, we had only the day before, they had to register and
Okay.
replicate the intakes.
Okay.
But it could be that these 2 participants had huge meat intakes, for example, 2 days before, the one that we were not controlling for, and then
Okay.
it was still excreted in during the intervention day then, but
Yeah. Was there any other information that you had from the individuals that would allow you to maybe say, yeah, these individuals were different, or did you not look at that?
it was not possible to find any correlation with these, for example, changes between these two conditions and other, for example, like if you have a higher lean mass, would be a higher change, but it was no correlation. We had, it was a correlation between the nitrogen excretion and the 3-methylhistidine excretion. But then it's maybe not easy to, I don't know what is the interpretation.
Fair enough. Yes. Now you used the word correlation a few times, and I'm not sure of whether you have a slide of figure 4 of paper number 3.
Yes, I do not have the correlation on my slide, yes.
No, but do you have a figure of a slide of figure 4 of paper number 3?
No, I don't think so.
If not, do you have your thesis there in front of you?
I have it.
I would like to take you to.
If you can think.
So it's on. Well, you know your thesis better than me, so you know where it is.
Yes, I have it.
So figure number 4.
Yes.
Where you plot the relationship between urinary nitrogen excretion and urinary 3-methylhistidine excretion.
Yes.
And those 2 data points there are in that figure as well, right?
Yes.
How confident are you that you have so we're looking here at the filled dots, the filled black circles.
Yes.
The exercise condition.
Yes.
How confident are you that there is a significant correlation? Because it seems to me very much that correlation coefficient is being influenced by those two. Because I didn't do the exercise, but if you would take those 2 out.
Yes, it would be almost.
I don't know. You may still have a significant correlation, but how confident are you to have included these in the analysis? And if you don't have a reason to exclude, you include them, but you don't provide any comment on that. So now that I bring this to the table, what is your response to that? That maybe that significant correlation is due to those 2 participants.
Yes, I think you're right. If we remove them, it would be maybe more flat and then disappear. But one of the things also we were out when we tried to drawing was also to see if there were a difference between the exercise and the rested condition. For example, if we were able to find one response, like for example, if this is well correlated in control, but then if exercise is not well correlated, then it would prove your point that people have individual responses. And the other way, if it's not correlated at all with control and there is with exercise, so maybe it's like maybe it's exercise induce some degradation, and then we are both able to see with both methods. So that's why we're also interested about the 2 differences or the 2 relationships in each condition. It would have been interesting to, without this point, it would seem that it would be really identical between the 2.
I mean, the good thing is you had a crossover design.
Yes.
So it is still the data from individuals for which you had observations in the control conditions. But as you did very nicely in your lecture this morning, you had the crossover design and the parallel group design. If this had been a parallel group design, you would probably have reported very differently on these observations.
Yes, absolutely. I think we would have been maybe a little bit more critical or tried to find the underlying explanation.
Yes.
with-
Okay. Okay, thank you. Let's move on to paper number 4. And if you can bring up the diagram again.
Design?
Yes. So we heard this morning that you can have very different protein sources. And in this particular study, you did go for whey protein.
Yes, and isolate.
And what was your rationale to go for this particular protein source?
Yes, it's because most of the studies have been based on whey protein, and also then, for example, looking at the insulin responses, the other study that looked at the insulin responses to protein-only drinks, where with whey protein or mixed of amino acids in smaller quantities. So then if the aim was to compare with them, then we had at least the same protein source. But also as we wanted to compare, again, for example, for the insulin response, the effect of protein-only drink versus a carbohydrate-only drink, and the plant-based proteins and the plant-based protein isolate, often they have a higher amount of carbohydrate still in the powder.
Yes.
So this one was not carbohydrate-free totally, but it was really small quantities. It was less than, it was only a few grams for the whole drink.
Okay.
So then we tried to have, it was not possible to have pure protein powder, but then we tried to find the one with the less carbohydrate and fat, and especially, carbohydrates.
And so my next question may be very naive, but I'm going to ask it anyway. So you have men and women in this study.
Yes.
Body composition is very different.
Yes.
So you may have a 70-kilogram woman and a 70-kilogram male, and body composition is very different. We make the body composition very different, but they have similar body mass. But then you provide them with the same amount per kilogram body weight. Is that a useful approach, or should you dose based on body composition parameters different than body weight? Because you're affecting, or you aim to affect something that happens in muscle, right?
Yes.
And so when people with similar body weight but very different body compositions may have different muscle mass. So how comfortable were you with the absolute dose of
or the
as a dosing strategy?
We had actually DEXA scans in this study, so we had data on the lean body mass of the participants. And for example, when we draw the figures on nitrogen excretion. So we were able to draw both in gram per kilogram of nitrogen, but also gram of per kilogram fat-free mass.
Okay.
And as in paper 3 also, when studying the effect of exercise, we draw also both these figures. And it was no big difference between these two, gram per kilogram of body weight and gram per kilogram of fat-free mass. And why we choose gram per kilogram of body weight then? We had to choose something, and we still think that it was a little bit better than, for example, the carbohydrate drink when they do like the oral glucose tolerance test. They give 75 grams of carbohydrates, whatever your weight.
Yes.
And I think it was not so, or it would have been a little bit even worse than what we did.
Okay.
So then we thought that at least doing the gram per kilogram and then expressing the excretion in gram
Yes.
per kilogram,
Yes.
then would be
Yes.
maybe taking more into account the differences between
Yes.
participants.
Yes.
And we still looked at the results with body weight and fat-free mass, and it was not changing the interpretation.
Okay. Okay. Because this would make life for the supplementation industry quite challenging if we can't dose based on body weight. That's easy because people
Yes, we also
know
think.
that
Yes, we need
instead
to
of
think.
oh, you need to do it based on the muscle mass that you have in your left toe or something. I'm making
Yes.
something up that is not real, but so it's very common. Another general question is because this morning in the lecture, you ended up your lecture with sort of recommendations on intake and so on. Obviously, and I applaud you on that the design of your studies were unreal. Nobody exercises in that way. I thought, why would you do 5 hours of this variation? Because if you do endurance exercise and high intensity exercise, you may have the interference of molecular pathways. You don't get the adaptations that you would like to have. So my question is, how much of the work that you did, and that's not only paper number 3 and 4, how much was blue sky, fundamental, and where, if it was not blue sky or fundamental, where do you see application for the work that you did?
Yes, that's a really good question, because then, for example, paper 2, it was the one that we had designed, and we had some studies from before indicating the effect of exhaustive exercise on performance. So then we were a little bit confident that it would work or lead to some results, and then we tried to control the most or what we could to get some result and be able to interpret. And then paper 3 and paper 4 were more our reflections after the results of paper 2, what we got. As for example, in paper 2, we had no difference in nitrogen excretion between carbohydrates and placebo, but we did not measure it at rest. So then we were not able to see if it's like, for example, there is a difference. It was increased from rest and then no difference between the treatments, or if there was no difference at all with rest and the two treatments. So then that's why we designed the paper 3, and it was maybe not our first focus then to have transferability as the first parameter. We wanted to go quite hard, or to have enough exercise to find a difference, and then, or at least that things that would be controlled enough and would lead to enough difference that can be seen, and then that we can use to interpret or to have a little bit background for the data on paper 2. And that's the same for paper 4. The main focus was not transferability, like no one wake up in the morning and just have a drink and then eat a lunch and nothing until 4. It was more being able to control most of the thing and then maximize the outcomes or what we were interested in, and try to minimize, for example here, as we had carbohydrate as a reference, other factors like energy intake or protein intake from prior days or prior day. So that's why it was designed. But yes, these two studies are following the paper 2, and then they are a bit unrealistic for normal people, but they were meant to to give us the best chances to find an effect, if there is one, to be able to interpret paper 2.
Yeah. So if I understood you rightly, you say it's a lot fundamental, blue sky, almost no application. I'm not sure where the funding was coming from for your studies, but there may be taxpayers' money involved in this, how it all gave you the opportunity to do this work. So the taxpayer will say, Matthieu, why did you do this? What can I do with these observations that you had? I'm a protein user. I have no clue whether I do the right thing, whether I take the right amount, whether I take it at the right time. The taxpayer is going to challenge you, the cyclist Czech taxpayer who uses protein supplements. What are you going to answer?
Now, this is really accurate, because before presenting the work today, we have a communication office, and then they ask me, what can we go, or what we need to publish an article about your thesis, what can be the key take-home message for normal people. And then I was a little bit in this situation that it was interesting, and then it's maybe mechanistically interesting and a little bit academical results, but then the transferability is not straightforward, I think.
Yes.
And everyone I talk to their main focus is always the protein requirements.
Yes.
And it's something that we did not investigate in these 4 papers.
Yes.
So I cannot give good answers to the taxpayers then.
No.
But I think this study is really interesting with the time resolution. We did not expect it to be that long, even if it's a high dose.
Yes.
So I think it should open to studies, maybe a little bit more realistic world study, but then for people training, or also people with intermittent fasting, I guess, it can also be good evidence that maybe it's not that severe not to eat or to have long period without. The body seems to be able to spread, or protein metabolism is not that quick.
don't take this question as that taxpayers should inform the design of the studies that we do. I really appreciate that we still have opportunities to do this work. So thanks to the Norwegian School of Sports Sciences to allow you to do this. That's just great. In paper 4, you have all the amino acids profiles. Well, you plot them versus time.
Yes.
And yeah, they all change, they all go up with
Yes.
different amounts, and obviously it is a balance between what appears in the bloodstream and what moves out of the bloodstream. Yes. Again, right? And then there was one, cysteine, who did not change at all.
Yes, it was
right?
no.
Was that expected, or was that surprise? All the others change, but not cysteine. And I don't know a lot about cysteine in order to figure out why that is, but maybe you know. So why did we not see that change with cysteine?
No, we didn't know either. I have my co-supervisor is at University of Oslo and is a little bit more in amino acid, and then we had discussions about. It was kind of expected that if you intake this amino acid, then of course you get more in the blood and it will be significant, but then the responses of different amino acids sometimes were a bit, as cysteine, difficult to expect, but also difficult to explain, like BCAA are expected, and glutamine also the one that can be used as substrate, for example, in intestine cells, then we could expect a little bit less in the blood, but then cysteine, I don't know.
Okay. And all the variation that you see, is that due to the different amino acid transporters, how they work?
Yes, or it's once again we only measure concentration, and I really like someone to measure the flux.
Yes.
Because also this concentration or the increase in concentration is significant, but then in proportion to the ingested quantity is also kind of small.
Right.
So then we can't conclude if it's not digested or digested over a long time, or if it's quickly absorbed and then quickly absorbed in which tissue.
Yes.
So it opens more questions than it gives answers in a way. So I'm really interested if someone can do these fluxes.
I do get that, yes. Another more general question, which I should have asked at the start, but here we are. I'm going to ask that now. So, and we can take not the exercise studies where a double-blind design is very useful. You don't want the participants to know that they're taking the good stuff. But you used also this was a crossover double-blind design.
Yes.
And what is the reason of doing it double-blind in your studies, but in general in sports nutrition studies or dietary supplementation studies? Why is that double-blind design important? And is it always important?
Yes, it was mostly for us not to influence the participants, us not knowing the treatment, because, for example, in this protocol, the participant had they had the treatment, and then the first time they ate then in food intake, and then it was all recorded on a paper.
Yes.
And then the next time replicating the same. And it was mostly not to, for example, if we see that maybe they got the protein and we want an effect of protein, pushing the one starting with protein, eating more during this day, or maybe giving kind of different instruction. I don't know if it would be so much in this study because it's not exercise,
Yeah.
but in the other one, you
Yeah.
can, especially with exercise and exhaustion,
Yeah.
it's if you push the participant, they
Yes.
can maybe
Yes.
go a little bit longer, and then
Yes.
it will be mostly.
I mean, I totally agree with you that when you can have bias in a testing environment for the outcome of that could affect the outcome of particular tests, then yes, a double-blind design is an accepted standard. But in the case of measuring, with all respect, blood parameters, I mean, if you give me a protein or a carbohydrate drink, I don't have an effect on my insulin response. I'm not biased to, I'm
Yes.
having carbohydrate now, I'm going to make a bit more insulin. Was there potential bias in your studies that you decided to do a double-blind design?
No, it was mostly, yes, as you say, you cannot influence so much your responses, and participants were mostly also, some participants were from the university and some outside, but then after the drink, most of them were sitting in a room until the lunch. So then there was like no difference in physical activity either. So then I don't think that knowing the treatment should have influenced so much the results.
Yeah.
At least in this study. For the exercise, I think it's nice at least to have.
I mean, it's
More
still, you know,
control,
I don't disagree with that you did a double-blind design, but sometimes when you measure just blood parameters over which you can't have control, yeah, you can argue whether a double-blind design is needed.
Yes. I
Right.
agree.
So I don't know which time I started. Soon finish. That is perfect timing. So we're going to soon finish. So we started with that quote,
Yes.
which I didn't read out aloud, but I did write down. There was considerable confusion in 1984. We are now in 2025. You've completed your PhD. You added more information to the body of knowledge on protein intake. I go back to the question that I asked you. Are we still confused, or is there less confusion nowadays in the area that you did your research in?
No, I hope that there is less confusion. But then I think every new studies open also new doors. So then maybe some of the confusion then are maybe we are finished with them, but then we find new results that are maybe unexpected, and then we open, for example, like the flux for amino acids. Yes, I think it opens new doors,
Yes.
and then still new studies are necessary, but we got some responses, some answers to the parameters, but yes, I think there's still some confusion or future works need to be done, yes.
Okay. Well, thank you very much, Matthieu, for giving me the opportunity, and thank you very much for your considerate responses. Thank you to the school again to allow me to be here. Thank you to the supervisor for the invitation. Thank you, Rector, for being here, and I wish you all the best in the future. Thank you very much.
Thank you.
Thank you both to Eva and Mark for excellent questions.
and for Matthieu for excellent answers. And the examination committee will now leave the room to evaluate the dissertation and make the final decision. I ask the rest of you to stay in this room, and I will announce the committee's decision within 5 to 15 minutes. So thank you. Oh, exciting times. The examination committee has found Matthieu Clauss' dissertation satisfactory. The committee's conclusion is anonymous. On behalf of the Norwegian School of Sports Sciences, I hereby award Matthieu Clauss the degree of Doctor of Philosophy, PhD in Sports Science. Congratulations! Well done. You will receive the diploma at the ceremony in August at the start of the next academic year. Now I will ask the committee, the head of the department, Klaus Madsen, and the new Doctor of Philosophy to join me in a procession out of the auditorium. I hereby declare the disputation for completed. Thank you.